While out netting in an exotic country, you discover a new fish species, the mohawk fish. You catch and observe about 100 of these fish, and you notice two distinct tails within this species. The square-tailed and the fork-tail. You want to see how often these occur in that population, but there's an issue. You simply do not have enough time in that country to be able to see how often these occur, and it comes to find out this fish is long living, so to be able to get enough data to be able to see how often these traits show up, you'll be pushing daisies. The other issue is you cannot run a chi-square because, again, with these generations, you simply do not have the time to do so. So you need a quick and easy model to be able to see how common and how much these different traits show up. And luckily there is the Hardy-Weinberg equation. With the Hardy-Weinberg equation, you are simply looking to see the allele frequencies in a given populations. There are two equations that go into this. P plus Q equals 1. P equals the frequency of the dominant trait, and Q equals the frequency of the recessive trait, with 1 equaling all alleles in the population. You also have another equation, P squared plus 2PQ plus Q squared equals 1. What is the importance of this? Well, when offspring are made, they have two alleles from the parents. So if we do this simple Punnett square here, it comes to find out you have one individual that is homozygous, dominant, two heterozygous individuals, and one homozygous recessive. So let's do a simple equation here to kind of get our heads around this concept. You have a total of 100 fish. 75 have square tails, 25 have fork tails. We write down our equations here. P squared and 2PQ represent the square tails, and Q squared equals fork tails. That Q squared is the most important part of this. Why? Because we do not know out of the homozygous dominant and the heterozygous how many of those fish fit into either one. So we know the frequency of the genotype of Q2, which would be 0.25. We take that and we can square root that Q squared, and we'll get our Q value. After the equation, we come to find out that P equals 0.5 and Q equals 0.5. So after that, we simply plug and chug into this big equation down here, and what we get is that everything is equal to 1. Now, once you've got your value, you can now put it into a chi-square test and be able to see the population, to be able to see if anything has changed. One thing to note with Hardy-Weinberg is that no population is ever at equilibrium. Why? Because you have to have no mutations, no genetic drift, large populations, and random mating. And in reality, this never happens, because populations are always under stress and always having to evolve to their environment. So simply what this model shows is that the population is facing evolutionary pressure, or is not facing evolutionary pressure. So, to give you an example, let's say our mohawk fish has smaller tail fins, the more forked tails. Maybe it makes them less noticeable to big predatory fish in the area that want to gobble them up for dinner. Or you start seeing more and more of the big old square. But it's simply just showing that evolutionary pressure is always affecting the population, but how much it's affecting it is what the Hardy-Weinberg equation is simply showing. Thank you for listening, and yes, I know my handwriting is bad.